How are you?
I'm good. Is this too much light?
Um, it is a lot of light. If you can, you're kind of shadowy.
It makes sense. You won't be able to see me.
It's okay.
And
Wherever
no way to block all the sunlight.
you.
Okay, this is gonna be a problem. I got an idea. I'll sit here on the shadowy side.
There you go.
But everything now is backward. Everything's backward now.
That same chair that you have behind you, I have that same chair in my room.
Huh?
I said the same chair, the little hanging one. I have that same chair in my room.
Cool.
Yeah,
You
I
got
like it a lot.
Pier 1? You got it from Pier 1, of course.
No, I got mine from Amazon actually, and it's a little bit different. It's not shaped kind of like an egg. Mine is shaped like a hammock, but it has the same stand.
Oh, the stand must have been from Pier 1 then. Oh, no, we got that one from Amazon, I think. I don't know. I can keep track of everything. Put the clips here.
Today I'm excited because we're going to be making a lava lamp, and that's one of my favorite activities.
I knew it. Even from reading the ingredients.
Oh, yeah.
I clearly know how the lava lamp was made. Because, seriously, there's always that same word. Because that's here. The water, oil, everything else. Put this here. And then we'll put this and this and this. And this right here.
Hey, Alexandra.
Yes?
Does it matter like what temperature the water is?
No, the temperature of the water doesn't matter as long as you just have water.
Oh no, my water! Got my actual computer. I hope you'll be careful. No. Can you hear me?
I can hear you.
Oh, perfect. Just one. I have a question.
What's the question?
So, does how big a magnet relate to how much magnetic force does it have? Like, does this have little less magnetic force than this, even though they're made of the same magnets?
It depends on the type of magnet that you have. So you can have a small magnet that's very powerful, and you can have a big magnet that's not that powerful. It just depends on the type of magnet. But since it's 2 or 3, we are going to get started with our activity today. So it's so great to see all of you, Kaveen, Malcolm, and Kendall. Today we are, Kendall, I like your background. It's very pretty. Okay. So today we are going to be building a lava lamp. So before we start, I'll just go over the materials. You need oil. I'm using canola oil, just like in the kitchen. A jar or a glass. Here's mine, just a cup. You also need Alka-Seltzer tablets and water, and food coloring is optional. So if you have it, awesome. If you don't, no worries.
Can you wait for a second?
Yep. All right, we're going to go to the next part while Kaveen comes back. Okay, Kaveen and Malcolm, are you guys here? Or did you have to go grab something? Okay, great. Thumbs up from Malcolm. Kaveen, all good?
Yeah, I'm all good.
Okay, first step we're going to do. Looking at your jar, you're going to fill it 2/3 of the way full with oil. So this is the height of my jar. 2/3 would be like about here. So 2/3 is more than halfway, but not all the way full.
Okay, let me just get my oil. Yeah. What about a tiny itty bitty water bottle?
Put 2/3 on your tiny itty bitty water bottle.
Yeah, I don't know how much 2/3 is though. Yeah. Yes. Yeah.
Yep, so here's my water bottle and it's filled 2/3 of the way with oil. Once you have the oil, you're going to fill your bottle the rest of the way with water. So up to the top, not so much that it overflows, but just the rest of the way with water.
Where are my gloves? Can you wait for a second? Let me just get something.
And you can give me a thumbs up once you have water and oil. That way I know we're all good to go.
Oh man. Oh my water. Hey. Oil. Oil has lots of viscosity. No doubt about that. Wait.
Is this too much?
That looks fine. You know, that looks okay. It's not going to overflow or anything, so that looks great. All right, so what did you notice once you added in the water? Was the water on top or on the bottom?
The water is less dense, so it's at the bottom.
Yeah, the water's on the bottom, yep. Due to density, last week we talked about density and how things that are more dense are going to be on the bottom and things that are less dense are going to be on top. So water is more dense than oil because it's on the bottom, and oil is less dense, so it's on top.
Really? But it's so thick.
Oh, well, that's more so viscosity than density. But we'll talk about that in just a second. So
crust oil. Oil is horrible.
Next, if you have food coloring, you can add it now. I don't have any food coloring for today, so I'm not adding any. But if you have food coloring, you can add in a couple drops.
Why don't we mix it? Oh, yeah. Well, hope this is enough. Well, I hope this is too much. I hope this is just enough. I'm gonna use a pipette just to see the bubbles.
Okay, so does everyone who wanted to add food coloring, you have food coloring?
Haha. Oh, this is cool.
All right, next is
bubbles are at the bottom. Ooh.
Yep, bubbles are at the bottom. Okay, next is the fun part. I'll just give everyone a few more seconds because I see some people adding in their food coloring.
Oh yeah, I haven't had my food coloring yet. Okay. Oh my gosh!
Okay, so now what we're going to do is the fun part. So go ahead and take out one Alka-Seltzer tablet.
No. It's so cool. My food coloring is like, it's so beautiful.
And once you have your Alka-Seltzer tablet, you can just drop it in and then watch what happens. All right.
I don't have a scissor, so can you wait?
There's mine. And once you add your Alka-Seltzer tablet, you can hold up your jar so we can all see what's happening. Okay, so once you added in the Alka-Seltzer tablet, what did you notice? Oh, I see Malcolm's. Look at that. It looks so awesome with the food coloring. Ooh, and Kindle's. Both you guys chose red. Look at that.
Oh no. Oh yay. I'm so glad these Alka-Seltzer tablets were so easy to break. My thing is way too small.
Okay, so this is pretty cool. So this is pretty cool, but clearly there has to be some science behind why we have all these bubbles, right? And the explanation is viscosity. Viscosity is a substance's resistance to flow. So syrup has a really high viscosity because when you try to pour syrup on your pancakes, the syrup flows very, very slowly. Water has a really low viscosity. Water is not very viscous. If I pour water, it pours pretty quickly, no resistance. So the other important thing here is something called immiscibility. Immiscibility means unmixable, two things that don't mix together, like water and oil. No matter how hard you try to mix water and oil together, they're not mixing, they don't like each other, it's not going to work out.
It's because of hydrophilic and hydrophobic. It's because hydrophilic and hydrophobic molecules. Hydrophilic means water love.
And hydrophobic means they don't like water. They don't want to interact.
And then oil has to be hydrophobic, and they don't connect. And since hydrophobic means scared water, when they go together, they just like move apart because it's scared of water.
Okay, thank you. So in a real lava lamp, there's one more substance. In a real lava lamp, one substance is water-based and the other is a waxy compound. So water is polar, and that means that it has an overall positive charge. Oil isn't positive or negative, but it is, like Kaveen said, hydrophobic. So it doesn't mix at all with water because the oil doesn't like water at all. It's not going to mix. In a real lava lamp, one substance is water-based and the other is a waxy compound. At the base of a lava lamp, there's a super warm light bulb. That's why lava lamps, you normally see them in the dark because they kind of light up because there's a light bulb in the bottom of the lava lamp. And the important thing about the light bulb is that it's very warm. It generates heat. All of the heat from the light bulb causes the wax to rise away from the bulb. Those are little bubbles that are rising up, the little wax blobs. And then as the wax rises up, it gets farther away from the heat source. So it gets cooler. And when it gets cooler, it starts to fall back down. And that's why you see the bubbles going up and down, up and down, up and down in a real lava lamp. The light at the bottom of the lamp warms the wax. And when things get warm, they expand and their density decreases. It becomes less dense and it becomes less viscous, so less resistant to flow or motion. So it's able to move. And then as the wax, what was that, Kaveen?
Can I say something, please? Oh, not this.
I'm going to finish explaining, and then if you want to say something, we'll do that. So gravity also pulls the wax down when the wax is at the top of the lava lamp. Gravity pulls it back down. And initially, the wax is more dense than the water, and it settles at the bottom of the lamp. But then the light bulb heats it up, the wax becomes less dense, floats up to the top, the wax gets cooler and becomes more dense, and it sinks back down to the bottom. That's why wax in a lava lamp just floats up and down, up and down, up and down. So since we have time today, we're going to watch a little video about someone taking apart a lava lamp and trying to figure out how does it work? What is the secret?
Oh my gosh.
What if the lava lamp explode?
That would not be very good. Since lava lamps are a lot of wax isn't too dangerous, but you definitely don't want a lava lamp to explode. Our lava lamps won't explode. There's no like chemicals in here. It's oil, water, and Alka-Seltzer tablet, so it's pretty safe.
Actually, yeah, a chemical reaction will. The bubbles will start to rise to the top, and seriously.
Okay, Kaveen, we're gonna play this video real quick. Let me know if you can't hear it. Everyone can hear the video? Thumbs up.
Yeah. Oh God. This is not attractive.
Oh.
It really does look like human fat. That's me and my boss opening up a lava lamp. Oh, we getting these noises, guys? Our goal was simple, to figure out what's inside. As it turned out, it actually wasn't simple at all. And that's because companies don't want you to know.
It's a formula that, has been pretty well guarded throughout time,
That's Brian Cass, Vice President of Product Development at Schilling, the manufacturers of Lava brand lava.
Oh, yes, Malcolm?
It's custody.
Yeah, come on. Up there it is. Enough water. Yeah. And the blue thingy, and then it just ooh.
Kaveen, do you mind pressing mute for a moment?
I can't. My hands are oily. That's the problem.
Okay, well, I just need to hear Malcolm because he was trying to tell me something.
I'm kind of skipping.
If you want, you can type it in the chat because I can't quite hear what you're saying. And I'll make sure to look at the chat. All right, I'm going to press play again.
Lamps. And true to his word, he wouldn't share the full recipe, but he did reveal some key ingredients.
Inside of a lava lamp, you've got wax, which is mostly paraffin wax. That's your lava.
Paraffin wax is a common wax made from petroleum. You can often find it in candles and cosmetics. But when we squeezed it in our hands, it didn't really feel like melted wax at all.
It sort of has the consistency of mashed pumpkin.
And what about all that liquid? Katzel said it's mostly water. And since wax doesn't mix with water, that makes a lot of sense. But as you can see, it's not just water. Yes, that extra coloring is partly for effect, but it also contains chemicals that prevent fungus from growing in the bottle. And of course, he did leave some things out.
There's a little bit of lava magic that we sprinkle inside there, but essentially it's liquid, it's water and wax.
That quote magic is actually really important because it's what makes lava lamps work the way they do.
You have these two liquids that are separate, but now you also want to have this effect where one of the liquids sort of dances around and goes up and down, and that has to do with the density.
He says that density is everything when it comes to lava lamps. When the lamp is off, the wax is slightly denser than the liquid around it, and that's why it sits at the bottom. And when most materials warm up, they expand and become less dense or lighter. That's what causes the wax to rise. And then as it reaches the top, farther from the heat source, it cools, contracts, gains density, and eventually falls back down. So what does this have to do with what's inside? Well, regular wax is normally lighter, not heavier, than water. So then what sort of wax is this stuff?
I suspect what you have inside is in fact not just plain wax. Most likely what you have is a mixture of wax and some additives. You add a little bit of this additive until it just starts to fall down. And that is when you reach that sweet spot. And now you can use the temperature to tilt the balance, either one side or the other. And so I suspect that most of the trademark secret is what kind of additive you want to add.
We asked Katzel about this, and he said at Lava those additives are actually in the liquid, not the wax.
At the end, you do a little bit of tweaking to the liquid to make sure that the wax is more dense than the liquid.
We may never know for sure what those special additives are, but a study published in 1996 may hold a clue. The researchers report they found that one lamp of an unspecified brand contained kerosene, which Sakana confirmed could make the liquid less dense. But whatever those magical additives are, they smelled really bad.
Oh, it smells terrible.
Exactly, yeah. This is not, plain with it is not helping the smell, as it turns out.
The smell is like making me nauseous.
So suffice it to say, we won't be opening another lamp anytime soon. And according to the company, neither should you.
All right, so that was just a short video that I thought was pretty interesting. And before this, I did not know how lava lamps were made either, so I thought it was cool to learn. All right.
Oh, and yeah, that same thing happens inside the earth. Cool hot
Viscosity?
rock
Density?
rises and cool rock. Yeah, the density thing, that happens with rocks. Hot rocks rise and then they cool down and they fall back down.
All right. Okay. So how does the actual lava, or how does our lava, oh, yes? Yes, Malcolm?
So I made this.
You made that?
And this is really just like if you shaking it. Yeah, I made it.
I'm sorry, yours?
Does this. And then it's like a cool down thing. So like if you're upset, and then you just look at it and you wait until all the oil separates from the water.
Yeah, that's a great idea. It is very calming, isn't it, to watch the water and oil separate? I like that. Okay, so how does our lava lamp work with oil and water? So we had two substances that combined, the tablet and the water. And that created a gas called carbon dioxide gas. And that gas is, the gas is shown as the bubbles that you see going up and down, up and down. And these bubbles carry all the color, all the food coloring to the top of the oil where they pop, and then the water falls back down. And this just keeps happening until all of the Alka-Seltzer tabs have reacted.
And when you add lots of water in them, like this, they start to jump. No, seriously, they start to jump. If you just like do it really fast, it's cool looking.
Are you using a pipette? Is that what you mean by adding water?
Yes, and it's really cool to watch. It's like a jump. You should try it out if you have a pipette.
Okay, I'll keep that in mind. All right, so
And
today we talked about viscosity. Who can tell me by raising their hand, or you can use a little raising your hand emoji, what is viscosity? What is viscosity?
What do you do after the lava lamp has reacted?
Ooh, Camille, I think there's a lot going on in your background, so I can't hear what you're saying.
Can you mute me, please?
Yes, I can mute you. There we go. Okay, so viscosity is a substance's resistance to flow. So some things that are like more thick may flow more slowly. Some things that are thinner solutions like water and oil may flow more easily and be less viscous versus syrup or glue. Those things are very viscous, have a high viscosity. Next, what gas was created? We talked about how we had the Alka-Seltzer tablet, which reacted with water, and what did that create? Any ideas? We had Alka-Seltzer tablet and we had water, and it made a gas, right? The little bubbles. What are those bubbles called? Oh, Malcolm?
Carbon dioxide.
Yes, you're right. It was carbon dioxide bubbles. Yep. Okay. And yep. Ooh, there we go. Carbon dioxide bubbles. And next, our next question. Oh, well, what is something new that you learned? And the only person that I haven't really heard from yet is Kendall. So Kendall, what's something new that you learned?
I learned that the oil doesn't really get colored unless you shake it. The water is the only thing that gets colored, and you're muted.
Yeah, I just realized, thank you. Yeah, that is true. The oil doesn't change colors as much. It's more so that the food coloring is like stuck on the carbon dioxide bubble, so it's not really interacting with at least the oil very much. Oh, Malcolm?
This is just a question.
Hmm.
If you want to put food coloring in water and oil, doesn't it make the water oil too? Like, so it won't mix at all?
Does
So yeah, the bubbles won't mix.
no, I think it does color the water. I think that's correct. Although we can try it right now. This container has water in it. I'm just gonna add, oh, no, we can't. I don't have food coloring. Never mind. Well, if you're at home and you still have water and oil and food coloring, try it and let me know. I'd be interested to see.
Yeah, so I did an experiment with it. There's like underwater fireworks. And basically that's all it is, oil, water, and food coloring.
Mm-hmm.
And immediately after, like when you put the oil and food coloring in, yep, immediately after you pour that into water, it will immediately change color.
Yep. Okay, well, if there are no more questions,
Change.
it will change. Mm-hmm. Yeah, I agree. Yep. Oh, Kendall, are you showing us what happens if you have oil and water? Is that what that was? Yep. Okay. All right, guys. So if there are no more questions, then I will see you on next Thursday for our last day of God Science. I can't believe it's already over, but I can't wait to see you all next week for a new activity. I can guarantee it's going to be fun. Bye, everyone. Have a great weekend.
I'm going to miss the next one. I won't be here.
No. Oh, okay. Well, it was great to see you
Gotcha.
again, Malcolm, and hopefully maybe another science workshop in the future.
Thank you.
All right. Bye, guys.
Bye.